On January 28, 1986, 73 seconds changed everything. 7 astronauts. Millions of witnesses. One explosion that shattered America's confidence in its space program. And in the aftermath, the most powerful aerospace organization on Earth scrambled to explain how something so catastrophic could happen. NASA had an answer ready. They called it an accident. A 1 in 100,000 chance. Just terribly bad luck. But there was a problem with that explanation. It was a lie. And one physicist, armed with nothing more than a glass of ice water and a piece of rubber, was about to expose it in front of the entire nation. This is the story of how Richard Feynman destroyed decades of institutional denial in less than 60 seconds. Not with complex equations, not with supercomputers, not with months of data analysis, but with the most powerful tool in all of physics, a simple demonstration that anyone could understand. And the lesson he taught that day extends far beyond rocket science. It reaches into the heart of how we understand truth, how institutions deceive themselves, and why nature always has the final word. To understand what happened in that hearing room, we need to go back to the morning of the Challenger launch. Florida's Kennedy Space Center was experiencing something unusual for that subtropical location. A genuine cold snap. Ice had formed on the launch pad overnight. The temperature at liftoff hovered around 28 degrees Fahrenheit. Now, you might be thinking, what does temperature have to do with a rocket explosion? Everything, as it turns out. But to see why, we need to understand a piece of engineering that most people had never heard of before, that terrible day. The Space Shuttle used solid rocket boosters, massive cylinders packed with fuel that burned to provide the initial thrust needed to escape Earth's gravity. These boosters were not single pieces. They were manufactured in sections and assembled, with joints connecting each segment. Think about that for a moment. You have a controlled explosion happening inside a tube, generating temperatures exceeding 5,000 degrees Fahrenheit and pressures that would crush a car. And you need to keep all that fury contained within segments that are bolted together. The seal between those segments relied on rubber rings called O-rings. Simple, flexible rubber gaskets designed to compress and expand, filling any gaps that might form as the metal flexed under the tremendous forces of launch. Here's where the physics becomes critical. Rubber is a remarkable material precisely because of its elasticity. Push on it and it compresses. Release the pressure and it springs back. This resilience is not magic. It comes from the molecular structure of rubber, long polymer chains that coil and uncoil, stretch and relax. But that molecular dance depends on temperature. Let us pause here and think about what happens to materials when they get cold. You have experienced this yourself, even if you never connected it to rocket science. Leave a rubber band in your freezer overnight. Take it out and try to stretch it immediately. What happens? It does not behave like rubber anymore. It feels stiff, resistant. If you pull too hard, it might even snap instead of stretching. This is not a flaw in that particular rubber band. This is physics. At the molecular level, temperature is motion. When rubber is warm, its polymer chains are constantly wiggling, vibrating, sliding past each other. This molecular activity is what gives rubber its flexibility. The chains can rearrange themselves when you apply pressure, then spring back to their original configuration when you release it. But as temperature drops, that molecular motion slows down. The chains become sluggish. They do not want to move anymore. At some point, the rubber transitions from a flexible, resilient material to something more like hard plastic or even glass. This transition temperature varies depending on the specific rubber compound. For the O-rings used in the Space Shuttle's solid rocket boosters, the engineers knew that temperatures below 53 degrees Fahrenheit were dangerous territory. Below 32 degrees, the rubber lost its ability to spring back quickly enough to seal the joint during ignition. And on the morning of January 28, 1986, the temperature at launch was 28 degrees Fahrenheit. Here is where the story becomes not just a physics lesson, but a profound study in human failure. The night before the launch, engineers at Morton Thiokol, the company that manufactured the solid rocket boosters, held a teleconference with NASA officials. These engineers had data. They had test results. They had seen what happened to O-rings in cold conditions. Well, and they were terrified. Roger Boisjoli, one of those engineers, later described how he fought like hell to stop the launch. He and his colleagues pleaded with NASA, "Do not launch below 53 degrees. The O-rings will not seal properly. The risk is unacceptable." But something strange happened during that teleconference. The managers at Morton Thiokol, under pressure from NASA, overruled their own engineers. One NASA official reportedly responded to the safety concerns by saying, essentially, "When do you want me to launch, next April?" Stop and consider what happened there. The people who understood the physics, who had done the tests, who knew the material properties of these rubber seals, were told that schedule mattered more than their expertise. The decision to launch went forward. The engineers were overruled, and 73 seconds after liftoff, hot gas burned through an O-ring that had become too cold and stiff to seal the joint. That gas became a blowtorch, cutting into the external fuel tank. The tank ruptured. The hydrogen ignited. 7 people died because rubber gets stiff when it is cold. 3 days after the explosion, President Ronald Reagan established a commission to investigate the accident. The Rogers Commission, named after its chairman William Rogers, included some of the most accomplished people in aerospace. Neil Armstrong, the first human to walk on the moon; Sally Ride, the first American woman in space; and a theoretical physicist named Richard Feynman. Feynman was not an obvious choice for an accident investigation. He was a Nobel laureate known for his work on quantum electrodynamics, not rocket engineering. His initial reaction to being invited was to resist. He had a principle, he later wrote, of not going anywhere near Washington or having anything to do with government. But his wife Gwyneth convinced him to join. Her reasoning was elegant. If he did not participate, there would be 12 people all going around together, following an official itinerary like normal bureaucrat. But with Feynman there, 11 would follow the schedule, while the 12th ran around checking unusual things. There was nobody who could do that like he could. She understood something essential about her husband. Feynman had spent his entire career asking simple questions that nobody else thought to ask, following chains of reasoning wherever they led, and refusing to accept explanations that did not actually explain anything. This was the man who, during the Manhattan Project, had annoyed security officers by finding flaws in their safe-cracking procedures. This was the physicist who learned to draw, to play bongo drums, to crack codes, to do anything that interested him with the same fearless curiosity he brought to particle physics. Now he turned that curiosity toward a disaster. From the beginning, Feynman found himself frustrated. The official proceedings moved slowly, filled with bureaucratic presentations and what he called the crazy acronyms that NASA uses. Officials testified in careful, measured language that seemed designed to obscure rather than illuminate. But Feynman was conducting his own parallel investigation. He visited at NASA facilities. He talked to engineers away from the official hearings. He asked simple questions. What were the O-rings made of? What happened to them at different temperatures? Who had final authority to approve or cancel a launch? What he discovered appalled him. NASA management had been estimating the chance of a catastrophic shuttle failure at 1 in 100,000. Think about what that means. At that rate, you could launch a shuttle every day for 300 years and expect to lose only one. But when Feynman talked to the actual engineers, the people who worked directly with the hardware, they put the odds closer to 1 in 100. Some said 1 in 50. There was a gap of 3 orders of magnitude between what management believed and what the technical experts knew. How does such a gap develop? Feynman identified the mechanism. A peculiar kind of wishful thinking had taken hold. If the O-rings leaked a little on one flight but nothing catastrophic happened, management concluded the problem was not so serious. Each successful flight, despite known issues, became evidence that the issues could be tolerated. This is like playing Russian roulette and concluding, after the first empty chamber clicks, that the gun must be safe. Feynman had a theory, but he needed proof. And more importantly, he needed proof that ordinary people watching at home could understand. Not charts, not equations, not technical reports that only engineers could interpret. He needed a demonstration. The key piece of information came through an unusual channel. Sally Ride, who was also on the commission, had seen an internal NASA document that the agency was not sharing with the public. This document showed 2 columns of numbers: air temperatures at previous shuttle launches, and the performance of O-rings at various temperatures. The correlation was undeniable. Colder launches showed more O-ring problems, but Ride was a NASA employee. Sharing internal documents could end her career. So she slipped the paper to another commissioner, General Donald Kutina, trusting him to find a way to use the information without revealing its source. Kutina was clever. He invited Feynman over for dinner at his home, and afterward took him to the garage where he was working on a car. As they looked at the disassembled engine, Kutina mentioned almost casually that the rings in his carburetor leaked when the weather got cold. Did Feynman think cold weather might affect O-rings? It was a head-slapping moment. Of course, cold makes rubber stiff. That was basic materials science. The question was how to prove it dramatically, publicly, undeniably. The day before a crucial televised hearing, Richard Feynman, Nobel laureate and one of the most celebrated minds of the 20th century, walked into a hardware store in Washington, D.C. He bought a small C-clamp for a few dollars. That evening, he also obtained a piece of O-ring material, the same rubber compound used in the Space Shuttle boosters, and he made a plan. Now, imagine yourself in that moment. You are about to go on national television. And 2, you have a theory about why 7 people died. You could present graphs. You could cite specifications. You could reference engineering reports that most viewers would not understand. Or you could show them. Feynman understood something that many scientists forget. The goal of explanation is not to demonstrate how much you know. The goal is to create understanding in someone else's mind. And the most powerful explanations are the ones that let people see the truth for themselves. February 11th, 1986, Docton. The hearing room was packed. Television cameras broadcast the proceedings to millions of viewers across the country. NASA officials sat at the witness table, explaining in careful technical language why the launch procedures had been followed correctly, why the decision-making process had been sound. Lawrence Malloy, director of NASA's rocket booster program, was testifying. He reported that nothing unusual had been noted before the launch, that all procedures had been followed. When pressed about whether anyone had concerns about the O-rings, he said he did not recall any. This was technically true in the narrowest sense. The concerns had been raised, but they had been raised through Malloy's organization and then dismissed. He had not received concerns because he had been part of dismissing them. During the testimony, commissioners passed around a scale model of the space shuttle. When it reached Feynman, he used the pliers he had brought to pull a small piece of O-ring rubber from the model. Then he did something that confused everyone watching. He dropped the rubber into his glass of ice water. The water had been provided by the wait staff. It was near freezing, close to 32 degrees Fahrenheit, roughly the temperature at the Challenger launch. Feynman let the rubber sit there while Malloy continued his testimony. General Kutina, sitting beside him, noticed what he was doing. The cameras were still on Malloy. Kutina whispered, "Not now." They waited. When Rogers called for a recess, Feynman removed the rubber from the ice water and examined it. It was stiff. Well, it did not spring back when compressed. The cold had robbed it of its essential property. After the break, Feynman pressed the button on his microphone. "This is a comment from Mr. Malloy," he said. He held up the piece of rubber for the cameras. "I took this stuff that I got out of your seal, and I put it in ice water. And I discovered that when you put some pressure on it for a while and then undo it, it does not stretch back. It stays the same dimension. In other words, for a few seconds at least, and more seconds than that. There is no resilience in this particular material when it is at a temperature of 32 degrees. He paused, letting the silence carry weight. "I believe that has some significance for our problem. Watch the footage of that moment if you can find it. Watch the faces of the NASA officials. Watch the other commissioners. No. Watch the chairman, William Rogers, scramble to contain what just happened. In 60 seconds, with no equations, no computer models, no technical jargon, Feynman had demonstrated what months of bureaucratic proceedings had failed to establish. The O-rings got stiff in the cold. They lost their ability to seal, and NASA launched anyway. Rogers tried to move on. That is a matter we will consider in the session we will hold on the weather, he said. But there was no containing it. The cameras had captured the demonstration. The American public had seen the truth with their own eyes. Later, during a break, Rogers was overheard saying to Neil Armstrong at a urinal, "Feynman is becoming a real pain in the ass." He was. That was exactly the point. Now let us step back and consider what made that demonstration so powerful. Because this is not just a story about rubber and cold weather. It is a story about how we know things, and how institutions can convince themselves they know things that are not true. Feynman's ice water demonstration worked because it was what scientists call a crucial experiment. It isolated a single variable, temperature, and showed its effect in a way that left no room for alternative explanations. But there is something deeper here. The demonstration worked because it cut through what Feynman would call cargo cult science, the appearance of rigor without its substance. NASA had charts. They had mathematical models. They had probability estimates carried out to impressive decimal places. 1 in 100,000. It looked scientific. It felt scientific. But it was, as Feynman later wrote, not really science at all. The agency had fallen into a trap that Feynman spent his entire career warning against. They confused the trappings of knowledge with actual understanding. Wow. They mistook successful outcomes for proof of safety, rather than recognizing them as evidence of good luck. Each time the shuttle flew, and nothing catastrophic happened, management felt more confident. But that confidence was built on sand. They did not understand why the O-rings sometimes eroded, and sometimes did not. They did not know why some joints showed more damage than others. They had data without comprehension. And when you do not understand the mechanism, you cannot predict the edge cases. You cannot say with confidence what will happen when conditions change. You are not managing risk. You are gambling. Let us talk about that probability estimate for a moment, because it reveals something important about how institutions can deceive themselves. 1 in 100,000 sounds impressively safe. It is the kind of number that reassures congressmen and budget committees. But where did it come from? Feynman investigated. He found that the number was essentially made up. Management had worked backward from a desired conclusion, rather than forward from actual data and understanding. They wanted the shuttle to be safe. Therefore, they estimated it as safe. The engineers, the people who actually built and tested the hardware, had no such illusions. Their estimates ranged from 1 in 50 to 1 in 200. Still risky, but honest risks that could be managed, debated, and weighed against mission objective. The gap between 1 in 100,000 and 1 in 100 is not a rounding error. It is the difference between fantasy and reality. And when organizations start believing their fantasies, people die. This is what Feynman meant when he wrote, for a successful technology, reality must take precedence over public relations. For nature cannot be fooled. Nature does not care about your press releases. Nature does not care about your launch schedule. Nature does not care about the political pressure you face from Congress. Physics operates according to its own rules, and those rules do not negotiate. Now you might be thinking, this is fascinating history, but what does it have to do with me? I do not design rockets. I do not work at NASA. Why should I care about O-rings and cold weather? Because the same pattern of self-deception that killed 7 astronauts shows up everywhere humans organize themselves to accomplish complex goals. Think about it. An organization develops a practice. The practice has a flaw, but the flaw does not cause immediate disaster. So the practice continues. Each successful outcome, despite the flaw, becomes evidence that the practice is acceptable. Warning signs are normalized. People who raise concerns are seen as obstacles rather than safeguards. Until the day when conditions align in just the wrong way, and the flaw becomes fatal. You see this pattern in financial institutions that convince themselves their risk models are more reliable than they are. You see it in healthcare systems that normalize unsafe staffing levels because disasters have not happened yet. You see it in software development when teams ship products with known vulnerabilities because those vulnerabilities have not been exploited so far. The Challenger disaster was not just an engineering failure. It was a failure of epistemology, a failure in how an organization knew what it knew and acted on that knowledge. And the cure is what Feynman demonstrated in that hearing room. Do not trust the impressive-sounding numbers. Do not accept complexity as a substitute for understanding. Find a way to test your beliefs against reality in a form so simple that self-deception becomes impossible. A glass of ice water, a piece of rubber, the truth. Feynman did not stop with the demonstration. Over the following months, he continued his investigation, even as cancer treatments took him repeatedly to Washington hospitals. He was determined, he wrote to his wife, to find out what happened and let the chips fall where they may. What he found went far beyond the O-rings. NASA had assembled the shuttle's main engines as complete units, without properly testing individual components. When something failed, they could not easily identify which part was responsible. This is like trying to diagnose a sick patient by examining the whole body at once rather than running specific tests on specific organs. The agency's quality control was inconsistent. Communication between levels of management was distorted, with bad news filtered and softened as it moved up the chain. The engineers who understood the actual risks were systematically excluded from the decisions that their expertise should have informed. Feynman wrote his own appendix to the official commission report because the main report did not say enough. In that appendix, he laid out not just what went wrong with the Challenger, but what was wrong with NASA's entire approach to safety assessment. The organization had convinced itself that it understood things it did not understand. It had replaced genuine analysis with paperwork, real testing with models that confirmed what management wanted to believe, honest risk assessment with numbers designed to satisfy political requirements. And he closed his appendix with that famous line, "For a successful technology, reality must take precedence over public relations, for nature cannot be fooled." There is a reason this story endures 4 decades later. It is not just because of the dramatic television moment. It is because Feynman embodied something essential about how science actually works. Science is not a collection of facts. It is not a set of equations. It is not even a method, really. Science is a way of not fooling yourself. And as Feynman often pointed out, you are the easiest person to fool. The organizations and individuals who fail most spectacularly are usually not trying to deceive others. They have first deceived themselves. They have convinced themselves that their beliefs are solid when they are actually built on wishful thinking and incomplete understanding. The antidote is what Feynman spent his life practicing. Relentless honesty about what you actually know versus what you merely believe. Constant testing of your assumptions against observable reality. Willingness to say, "I do not know," when you do not know. And perhaps most importantly, the courage to follow the evidence wherever it leads, even when the conclusions are uncomfortable, even when powerful people prefer different answers, even when your own previous beliefs must be abandoned. In that hearing room, Feynman was not being clever. He was being honest. He was not showing off his Nobel Prize intellect. He was doing what any curious person could do, asking a simple question and finding a simple way to answer it. Does rubber get stiff when it is cold? Here, let me show you. 7 people died on January 28, 1986, Stockstein. Krista McAuliffe, who would have been the first teacher in space. Francis Scobie, Michael Smith, Judith Resnick, Ronald McNair, Ellison Onijuka, Gregory Jarvis. They died because an organization convinced itself that it understood something it did not understand. And 17 years later, it happened again. On February 1st, 2003, the Space Shuttle Challenger broke apart during re-entry, killing all 7 crew members. The immediate cause was different: damage to heat shield tiles from foam insulation that struck the wing during launch. But the underlying cause was hauntingly familiar. Once again, NASA had observed a problem and normalized it. Foam had been striking the orbiter on previous flights. Nothing catastrophic had happened, so the problem was deemed acceptable. Once again, engineers raised concerns that were dismissed by management. Once again, an organization's faith in its own procedures proved unjustified. Feynman had died in 1988, but his appendix to the Challenger report was cited extensively in the Columbia investigation. The same patterns he had identified were still present, still deadly. Nature cannot be fooled, and neither can physics be satisfied with institutional convenience. So what does this mean for us, sitting here far from rocket launches and commission hearings? It means that the most important skill you can develop is not the ability to sound impressive. It is the ability to actually understand things. It means that complexity is often the enemy of truth. When someone explains something to you in language so complicated that you cannot follow it, the problem might not be your intelligence. It might be that they do not actually understand it either. It means that the most powerful question you can ask is often the simplest one. Does this really work the way people say it does? How would we know if we were wrong? Richard Feynman spent his career demonstrating that the deepest truths of physics could be explained simply, not because physics is simple. It is fantastically complex, but because genuine understanding always leads to clarity, while confusion is often a sign that understanding has not yet been achieved. The ice water demonstration was not a trick. It was the purest form of science. A question, a test, an answer that anyone could see. And in a world increasingly filled with complexity, with experts speaking in jargon, with organizations defending their positions through elaborate arguments that obscure more than they reveal, we need that kind of clarity, more than ever. Feynman once said that he could live with doubt and uncertainty. He did not have to know all the answers. He had approximate answers, possible beliefs, and different degrees of certainty about different things, but he was not absolutely sure of anything. This might sound like a weakness. In fact, it is the opposite. It is the source of all scientific progress. When you admit what you do not know, you become capable of learning. When you pretend to certainty you do not possess, you become immune to evidence that contradicts your beliefs. NASA's management was certain the shuttle was safe. The engineers were uncertain. The certain were wrong. The uncertain were right. There is something beautiful about that piece of rubber in the ice water. It is humble. It does not require advanced degrees to interpret. It does not hide behind technical language. It simply shows what happens when rubber gets cold. And in doing so, it teaches us something about how to live in a world full of complex systems and confident experts. Ask questions. How? Test claims. Look for the simple demonstration that cuts through the noise. The universe operates according to laws that do not care about human preferences or institutional politics. But those same laws are discoverable by anyone willing to look honestly at how things actually work. That is the gift of physics, not a set of answers, but a way of finding them. Not certainty, but something better. A method for distinguishing what we actually know from what we merely believe. Richard Feynman walked into that hearing with a glass of ice water and a piece of rubber. He walked out having shown the world what intellectual honesty looks like. Not as an abstraction, as an act. And if you take nothing else from this story, take this. The truth is usually simpler than the lies told to hide it. Look for the simple test. Ask the obvious question. Trust your ability to understand if the explanation is honest. Nature cannot be fooled. Neither, in the end, could Feynman. End card. Channel otro visuale.